Okay, so let's define this. This is the frequency of the nth harmonic. And it would be measured in hertz. This is the harmonic number. This is the speed of the wave on the string. Still measured in meters per second like speed always is. And this is the length of our string. Still measured in meters. So for a stringed instrument, if we want to change, if we want to tune it, what we're doing is we're tuning it to, what does a tuner usually measure in? Which is frequency. All right, so by changing the what, when you twist it and turn the knob, what are you changing? Do you move the tension? We didn't move the pegs or the bridge or whatever it's called that holds the strings at the bottom. We didn't move those, okay? But we have changed the tension. So when we tune it, we want to change the frequency, and frequency is directly related to velocity, and so the speed of a wave on a string is going to depend on some properties of the string. First of all, if you tighten that string, what's going to happen to the frequency? It gets higher. So that if the velocity is directly related to the frequency, then the tension, the force of tension in the string, has to be directly related to the velocity. Now, are all strings created equal? Tell me about the strings. What are they? Some are fat, some are skinny. How do the fat ones sound? Low. And how do the skinny ones sound? High. So what's then the relationship between the mass of our string and the frequency? It's indirect. So it's actually an indirect relationship with our speed. Now, the symbol, or what we're actually measuring, is not just the mass of the string, but the mass per length. And unfortunately, the symbol most often used for mass per length is mu. And usually this is going to be, or SI units, it should be in kilograms per meter. So, but because most strings are small and light, a lot of times the mass per length will be given in grams and centimeters. And what do you need to do? You do need to convert it, because what is the force going to be measured in? Newtons, and a newton is a kilogram meter per second squared. So a newton is already in kilograms and meters. So we do have to make sure that we convert. And then this should be a square root function. And if it were super important that you could derive that, we would have. But mostly just talking through it will work just fine. So this V is the speed of the wave in a string. Ft is the tension in the string. And again, tension should be measured in newtons. The speed is meters per second. And mu is the mass per length. And it should be in kilograms per meter, so be careful. So the other instrument we can get a standing wave in is a woodwind, or like a flute, or clarinet, a trumpet, something that moves not a string, but what? Air. That's right. So we can study pipes. Pipes also have a standing wave inside. You can blow across the top of a bottle, right? It's got some water in it, and it will make a note. Sometimes it's not tuned, but it'll make a frequency you can hear a sound. All right, so we have two different kinds of pipes. We can have open pipes. That means they're open on both ends. Or we can have open closed pipes, which means they're closed on one side. So an open pipe, both ends are open there, so I'm going to leave them not shaded. For my closed pipes, I just shade one end. All right, so because you can't see air molecules, the best thing for us to do is look at this little app. Okay, so this represents the edges of the pipe. We've kind of like cut the pipe in half, and the blue dots represent the air particles. And so as the air moves, it's moving the most at the ends. And when a particle vibrates the most, is it a node or an antinode? It's an antinode. So we have an antinode and an open end always. Always open end antinode. Okay? And nodes and antinodes have to alternate. So if we have an antinode here and we have an antinode at the other end, we must have a node in the middle. And this is our most basic, simple wave we can possibly get. Now, drawing these air molecules vibrating longitudinally is like impossible. Okay? So we represent the wave in the pipe as part of a sine or cosine graph. So it's not that the air is vibrating up and down. It's still vibrating back and forth longitudinally. Okay? But it's hard to draw that. So we just draw it as a sine or cosine graph. Okay? So let's draw that simple wave in our pipe. So either it's like this or it's like this. This is the first one we can make. The first one we can make. All right, so how much of a whole wave, now think about your sine wave reference right here. Okay, how much of a whole wave is in that pipe? Half. Yeah, we start from a positive amplitude and we go to a negative amplitude, and how much of a whole wave is that? Half. And speed is still frequency times wavelength. Up here, wavelength is still 2L. So that means that our velocity is frequency times 2L. And our frequency is then V over 2L. Okay, so now that I've gone up to the next higher harmonic, notice that we have our antinodes still at the open end, and we have to alternate nodes and antinodes. So if I want to add to this wave form, I have to have an antinode node, so there's barely any movement right here with our particles. We got a lot of movement here, very little right there, lots of movement there. So then we would represent the wave, the longitudinal compression wave in this pipe, as being this shape in our pipe. All right, so let's look at this length here. This length has a whole wave in it. Same song and dance. If speed is frequency times wavelength, then the speed is frequency times L. Therefore, the frequency is speed divided by L. Okay, can I pause here and just see if these guys are beginning to look familiar? Do you think 2 is enough? Our first one, we had what, N? Nope. We had V over 2L. The second one we just did was V over L. What's it beginning to look like? It's beginning to look like the string. And that's exactly right. The string is symmetric, meaning it was fixed on both ends. And the open pipe is symmetric because it's open on both ends. So that's why they behave similarly. So then we could write an equation for the nth harmonic in an open pipe as NV over 2L. So this is the open pipe. Now this is the length of the pipe. And that would still be measured in meters. This is not the speed of a string because it's not a string. What's inside this pipe? Air. And air, and what's the point of playing an instrument? What do we hear? Sound. So it's the speed of sound. And then this is the frequency of the harmonic. And N is the number of the harmonic.